Here are the mock exam solutions. I will be going over these in class, but if you want to go ahead and view the video beforehand and so you'll be ready to ask your questions, that might be a good idea. For number 1, you're asked to find f prime at 2, and most everybody did great on this. You do need to find f prime at x first, and that's going to give us 3x squared minus 2x plus 1. And now we need to find f prime at 2. So that's going to be 3 times 2 squared minus 2 times 2 plus 1. That's right, folks. I'm at school. Woohoo! And so f prime at 2 is 12 minus 4 plus 1, so it looks like you're going to get 9. So my answer should be B. Now for number 2, this problem was omitted because in order to do this, we would have to separate this dx, multiply it over, and really we need to know, well, if I took the derivative and got tangent x, what did I take the derivative of? And this one is a little bit more difficult. A lot of people wanted to choose B. That's the derivative of tangent x is secant squared x. But this is saying, hey, my final answer after I took the derivative was tangent, and we don't know what that is yet. Actually, it's going to be negative natural log of absolute value of cosine of x, and then plus c. And then we would take that negative and we could move it up to be the exponent, and cosine to the negative 1, or 1 over cosine, would be secant. So the correct answer here is C, but it wasn't something you had to know for this exam. Okay, so for number 3, what is the average or mean value of this function here over this closed interval? And a lot of people remember you need f at b minus f at a, or f at 2 minus f at negative 1 over 2 minus negative 1. And so we need to plug in 2 and see, and it might be easier to come down here and find, well, what is f at 2? Well, that's 3 times 2 to the third minus 2 squared. So that's going to be 3 times 8, 24, minus 2. So that's going to give me 20. And then f at negative 1, that's going to be 3 times negative 1 cubed minus negative 1 squared. And so that's going to give me negative 3 minus 1. So that's going to give me negative 4. And now I'm ready to plug into my formula. F at 2 was 20 minus f at negative 1 was negative 4 all over 3. And so that's going to give me 24 over 3, which is 8. So my answer choice here is C. Okay, number 4. If the limit as x approaches 3 of f of x equals 7, which of the following must be true? Now, please remember, if we know the limit value of something, we really don't know a tremendous amount about that function. That's just something we have to be careful on. And so, let's see, if x is 3 here, and one of my favorite graphs to draw in this situation would be a graph that would have a hole in it. And so here's a function, and let's see, I'm going to call this y value up here, obviously 7. And so notice my limit as I approach 3, as I'm getting closer to 3 from the left and from the right, my y values are getting closer and closer to 7. So this is a picture of what might be going on with this limit. But keep in mind what could happen here. Now, as x approaches 3, we're talking about what our y values are approaching, not equal to. It's just what are they getting super close to from the left and from the right. So let's look at this first statement. f is continuous at x equals 3. From my drawing, we see that doesn't have to be true. We do not have to have a continuous function for that limit to exist. So we're going to cross that out. Well, if we don't have to be continuous here, we certainly are not guaranteed differentiable. And here, this is saying that really you filled up this hole, that over here at 3, my y value is 7, but it doesn't have to be. We could have a for sure value for 3 down here at, let's say, 4. So really, this doesn't have to be true. F of 3 could equal 4, but I still have a limit value of 7. So honestly, none of these have to be true. Not a single one of them. So just knowing the limit value as x approaches a certain number equals 7 or whatever, it's not going to tell you a tremendous amount. The only situations where that would be true is if our limit was x was approaching infinity. We could talk about asymptotes, or if the limit wasn't defined, then we could talk about breaks in the graph or maybe some kind of asymptote or vertical asymptote. And number 5, this graph, the graph of which of the following equations has y equals 1 as an asymptote. Well, if y equals 1 is our asymptote, that's talking about a horizontal asymptote. And so let's think about this. If y equals 1, that's the case we talked about where we had Betsy. In other words, my bottom exponent equals the top exponent. We're talking about the highest power. Then I have a ratio of coefficients. So looking at A, we're not going to have a horizontal asymptote of 1 here. Here with sine, no, not necessarily. Well, let's look at C. If we did the limit because we can do that for horizontal asymptotes, we can talk about the limit as x approaches infinity of my function of y. I need to get an answer of 1. Let's revisit part B for a minute and make sure we see here. If we drew our sine curve, remember our sine curve does this. It's oscillating. And remember, if this was drawn better, it oscillates between +1 and -1. Oh, that's terrible drawing. Y'all use your imaginations. And -1. So really this limit as x approaches infinity, if we talked about sine of x, well, that limit is going to be oscillating between a 1 and a -1. So here we have to be careful with that. Now, what about as the limit as x approaches infinity of y if we talk about c? Well, notice c, we would pick out the highest exponent on top and the term that goes with it, and the same for bottom. And notice here, this is a Betsy, the bottom equals the top, so we look at the ratio of the coefficients. In other words, we look at x over x, and that gives me 1. So pretty sure my answer needs to be C. If we did some more investigating and talked about as x approaches infinity for D, this would be what we called a bigger on top, undefined. Here, my exponent's bigger on top. I don't have a horizontal asymptote, but I would have a slant asymptote of some sort. And for E, we could rewrite this to be 1 over e to the x. That's what that negative x is implying. And as x approaches infinity here, well, that's just going to go to 0 for that one. So we could say we had a horizontal asymptote at 0 for E. So number 5, answer choice has to be C. All right, so for number 6, this is really talking about the definition of a derivative. And we do need to go back and remember at the very beginning of the school year, we talked about the limit as h approaches 0 of f of x plus h minus f of x all over h as h approaches 0. We talked about this, and this was really talking about the slope of a secant line, but our h, or our distance, was growing or tending towards 0. So that would make that secant line become a tangent line. And when it was all said and done, we saw that this generated the same answer as the derivative. That's why we call this the definition of a derivative. Now, we wouldn't have to actually work out this entire limit. What we need to do is find, well, where is f of x always going to be sitting? And notice in that definition, or you can think of it as a big formula, right there is where your f of x is sitting. So if f of x is equal to sine of x, and this is asking us for f prime of x, well, f prime of x, or the derivative of cosine, or I'm sorry, of sine is cosine. So my answer is D. Number 7, this is talking about n approaching infinity. So we're really talking about a horizontal asymptote. And that horizontal asymptote is going to be where we talked about Betsy, Bobo, and Botu. And notice for this one, we're going to have a Betsy. If we find the highest exponent and its term on top, that's a 3n cubed over, and the same for the bottom is going to be n cubed. Notice we talk about the ratio of the coefficients. The bottom equals the top. Those n's, you could think of those as canceling each other out. And so my answer is 3. And do remember that is the same as a horizontal asymptote. Alright, so number 8, we're talking about the equation of a line tangent to this graph at a particular point. And notice that my function looks like I'm going to have to do the quotient rule. So let's go ahead and find y prime. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And so the bottom squared, 3x minus 2, all squared. And so now I need, for this to generate the equation of that tangent line, I need the value of y prime when x equals 1. So we're going to plug in a 1 everywhere I see an x. So that's going to give me 1 times 2 minus 5 times 3, and that's going to be all over 1 squared. And so if we keep working on this one here, we notice we have 2 minus 15, which is going to give us negative 13 over 1. Now, when we're writing this equation, then we are going to need to put it into our point slope form. And that's our y minus y1. Well, y1 is 5 equals m, we just found to be negative 13, times x minus x1, which is 1. And notice that the way this is written, x and y are together on one side, so I need to go ahead and do some rearranging here. So I have negative 13x plus 13, and then let's see, we're going to go ahead and move this 13x over and then the 5 over to the other side. So we end up with 13x plus y, and then that equals 18. So it looks like my answer should be B. All right, with number 9, we need to find f prime at x. We need to do the derivative and then plug in 0. So let's see what f prime looks like. This is a good case where we're going to have to do the chain rule. We have an exponent out here, so we have a function raised to a power. So let's see, we have 2/3 times x squared minus 2x minus 1, and then 2/3 minus 1 is negative 1/3, and then times the derivative of the inside, so 2x minus 2. And now let's see, we need to see, well, what is f prime at 0? So we have 2/3 times, well, let's see, if I plug in 0 everywhere, I'm going to have -1 to the -1/3 times -2. And let's see, to simplify here, -1 to the -1/3. This negative up here is indicating reciprocal, and the power 1/3 means cube root. And so really 2/3 times the cube root of -1 is still -1, and then times -2. So it looks like when it's all worked out, we should have a positive 4/3. Hey, here's another problem dealing with vertical and horizontal asymptotes. Now, when we talked about a horizontal asymptote being y equals 2, again, that's going to be in my case of Betsy, bottom equals top, so it's a ratio of coefficients. So if I look at this problem here, notice y would equal ax over x. And so notice here, a would have to be, if we reduce that, we have y equals a. And we're also told that y equals 2 for this problem. So that means that, of course, a has to be 2. So there's part of my a plus c. And now let's look at, let's see, the vertical asymptote is -3. So for my vertical asymptote, that comes from setting the denominator equal to 0 and solving for x. So notice x equals -c, but we also know that x is equal to -3. So it looks like from this we can say, well, c has to be 3. So here c is 3, a is 2, so the sum of a and c would have to be 5. Okay, so for number 11, we have a function that is continuous on the closed interval from 2 to 4, and as soon as it starts giving me information like this, I like to graph these. And so let's see, f at 2 is 10, so that's the order pair 2, and then up to 10. So I have a point here, and then I have 420, so let's go over to 4 up 20. Okay, so I need to extend this line a bit. So here's 10, here's 20, and here's 2 and 4. And all I know is that I'm continuous over this closed interval from 2 to 4. So that means that all of these values are accounted for. These points are connected. Now, I don't know how they're connected, what it looks like. I just know that that graph is defined everywhere, or is continuous, not just defined, sorry. So which of the following is guaranteed by the intermediate value theorem? So the intermediate value theorem, if f is continuous on this closed interval, that has us looking at our y's and our x's, and really it's coming in from the y's point of view. It's saying if I have a y value through here for all of these y values, then I have x values to go with them, which kind of makes sense. Since you're continuous, you have no asymptotes or hole in the graph, and so it's kind of like, well, okay. Well, let's look at A. A says f of x equals 13 has at least one solution in this open interval. So what that's saying is my y equals 13, for y equal to 13, which would be somewhere in here, there has to be an x down here. Well, yeah, let's see, 13 is definitely between 10 and 20, and my function is continuous. So yeah, A has to be true. There has to be at least one solution there. Now, let's look at B. 15, yeah, 15 is between 10 and 20, but the intermediate value theorem doesn't say that the x that goes with 15 has to be equal to 3. That x can be equal to any value between 2 and 4. So that's a little too specific for IVT. And intermediate value theorem tells us nothing about derivatives, and so that kind of gets rid of the rest of these. So the answer choice here would be A. Okay, so for number 12, we have a particle that moves along the curve xy equals 10, and we have x is 2, dy dt is 3. We're looking for the value of dx dt. So hopefully, with the idea the particle is moving and looking at the given information, you realize you're going to have to find the derivative of this with respect to time, and we need the product rule here. So make sure you include the product rule. So when we go through our product rule, we have the first times the derivative of the second, and the derivative of y is 1, but we have to note that we took the derivative of y with respect to t. So we have first times the derivative of the second plus the second times the derivative of the first, and by the same reasoning we have 1 dx dt, and then all of that equals 0, as the derivative of a constant is 0. And now let's plug in what we know. We know here x is 2. We know dy dt is 3, plus, well, we need a y value. We're not given a y value, but we know a relationship with x and y is equal to 10, and we know x is 2. So really, we could say, well, if I know x, y is 10, and if x is 2, well, then it stands to reason that y has to be 5. So I know that's going to be 5 times, and dx dt, well, that's what we're looking for. And so after all of our algebra magic, it looks like dx dt is going to be equal to negative 6 over 5. So that should be answer choice B. All right, number 13. With these problems, and we've seen quite a few of them, you need to make sure you're looking for which statement is false. Now, for a limit to exist, remember you talk about the limit as x approaches some number from the left, and then you have to make sure that value is approaching the same, x as is approaching the same from the right. So you're tracing in both sides. Now, it's not necessarily saying equal to, because if we do the equal to, that's where we get messed up with these holes in the graph. So let's look at the answer choices they gave us, and let's trace through and see. So for the first one, it's talking about the limit as x approaches 2. Does that exist? Well, as we approach 2 from the left and from the right, notice we are approaching the same value. Now, there's a hole in the graph, and that's okay because we're not talking about equal to, we're just talking about approaching. So does this limit exist on A? Absolutely. Okay, so let's look at another one. The limit as x approaches 3. So we approach 3 from the left, my function's moving upward, and from the right, we're approaching 3. And notice we are approaching that same value up here. So does that limit exist? Yes. And so we're going to continue this all the way through. So look at part C. The limit as x approaches 4. Well, the limit as x approaches 4 is moving from the left, is moving here. But notice from the right, it's way up here. Notice we're looking at two completely different y values here and here. So the limit as x approaches 4 would not exist. So my answer here is C. Okay, so here we need the derivative of f of g of x. So with this derivative, it looks like we have a function inside a function, so you need the chain rule. And so with the chain rule, we deal with the outside function. We do the derivative of the outside times the derivative of the inside, so g prime at x. And so we want this value when x is 3, so now we can plug in. We say f prime of g of 3 times g prime at 3. And now let's go look at our functions. So g at 3, well, g at 3, well, that's going to be 3 times 3 minus 2, so 7. So here I'm talking about f prime of 7 times, well, what's g prime at 3? Well, g prime at 3, well, what does g prime at x look like? Well, that's just, here the slope of that line are 3, so we're going to have 3 here. So now I need to know, well, what does f prime of x look like? And this is, again, chain rule, because all of this function up here is going to be raised to the 1/2 power. And so whenever I do my derivative, I'm going to have 1/2 times x squared minus 4 raised to the negative 1/2 times the derivative of the inside. And those 2's will certainly cancel. And so, well, what does f prime at 7 look like? Well, let's see, that's going to be 7 squared minus 4, so 45 to the negative 1/2, and then times 7, because we have an x out there. So f prime at 7, negative 1/2 means I need the square root of 45, and then I need the reciprocal. Well, the square root of 45, we can break that down to be 9 times 5, so that's going to give me 1 over 3 root 5 times 7. So all of this, that is equal to f prime at 7. So if I come back over here, I have 7 over 3 square root of 3, and then times the 3 that was already there. So it looks like I get an answer of 7. Oh, that's not a 3. Y'all, I messed up. That should be a 5. Oh my goodness. So let's make that a 5. So that's going to be 7 over the square root of 5. So that's going to be answer choice A. Okay, so for 15, we have, let's see, the graph of the function f is showing in the figure above, so always circle which function you're looking at. For which of the following values of x is f prime at x positive and increasing? Positive and increasing. So let's think about this a minute. If f prime is positive, then we're looking for where f is increasing. Interesting. Okay, and then also let's talk about, well, let's see, f prime positive and increasing. So if f prime is increasing, then by the same idea earlier, that's going to imply that, let's see, f double prime is positive. And if f double prime is positive, that implies f is concave up. Wow, that is crazy. All right, so let's make sure we got this. So f prime is positive, and we're looking for the graph of f. F prime positive, that happens when f is increasing. And then I want to look at where f prime is increasing. Well, and again, I'm just looking at f. I'm only given the graph of f. So if f prime is increasing, then f double prime, by the same reasoning we just used, has to be positive. And then we also know that if f prime is positive, then f is concave up like a cup. So let's see, that's definitely not A. So let's find where we're increasing. Well, over here at point C, my function is increasing, but we're concave down. So it can't be C. D is decreasing. So let's look at E. E is on the path that's increasing, and we're concave up like a cup. So it looks like my answer is going to be E. All right, so now let's look at 16. The graph of f prime, the derivative of the function f, is shown above. Which of the following statements must be true? So notice here's the graph of f prime. So let's look at our first statement. F has a relative minimum at x equals 3. Well, let's go investigate. And remember, that's talking about the original function. At -3, we're sitting right here. So what happens around -3? Well, f prime goes from negative to positive. So that tells me that the original function f went from decreasing to, let's see, f is now increasing. So decreasing to increasing, and then we see that f prime right there is 0. So yeah, Roman numeral 1 is correct. So let's see, gosh, that throws out C and B. But we've still got to investigate a little more. So let's look at, let's see, 2, point of inflection, or 3, the graph of f is concave down over the interval from 0 to 4. Well, let's see, I would talk about f is concave down. If I'm looking at the graph of f, well, if f is concave down, that means f double prime is negative. Well, if f double prime is negative, then that's going to imply that f prime is decreasing. So let's go look at our graph. Is my graph from 0 to 4? So I'm looking from 0 to 4, so I'm looking right through here. Is my graph decreasing over that interval? Well, it is. It's decreasing over this interval here. It is moving downward, so that one's correct. So it looks like my correct answer is E. Now, we could have very easily taken and looked at number 2, but to me it would be just a lot easier to look at the third one because of the concavity, and knowing this relationship here is just a little bit easier. Okay, so for 17, let's see, the graph of f prime, the derivative of f is shown in the figure above. So this is the graph of f prime again. F has a local maximum. Local maximum is the same thing as relative max. And so f has a relative max. Well, when does that happen? Well, the first thing we need to look for is f prime is 0 because that's a critical point. So that's going to happen here and here. And for this to be a local max, f prime has to go from positive to negative. So on my graph, where do I go from above the x-axis to below the x-axis? Well, that looks like that's going to happen here at 1. So my answer is C. Okay, so let's see. For number 18, again, same idea here. And except for now, with this one, notice that we have the second derivative. Okay, and let's see. Over what intervals would f be concave down? So let's see. Graph a second derivative. So when the second derivative is negative, that implies that f is concave down. So I need to look graphically. That's going to imply below the x-axis. So where would my graph be below the x-axis? Over what intervals? Well, again, notice we're in a closed interval. So it looks like from -2 to 1, that area is negative. So -2 to 1, so that gets rid of all of those. And then from 1 to 3, yep, you're below the x-axis there also. So it looks like for 18, my answer should be E. Okay, number 19, most everybody got this one correct. This is a very good problem. At what time t does the bug change directions? Well, notice here we are given the graph of velocity. And when velocity is positive, remember our bug would be traveling to the right. And when velocity is negative, particle or bug in this case is traveling to the left. And if you want to know where you're changing directions, this is where we're actually crossing the x-axis, not just touching the x-axis, but crossing over. And so that time would be at C. All right, and then our last question on this, the equation of the line tangent to the graph of cosine of 2x at x equals pi over 4. So remember our general form that we need, and so x equals pi over 4. Well, notice all of our answer choices have x being pi over 4, so I can't cross that out. So we could eliminate some answer choices by finding y. So let's go ahead and plug in and find y. So y equals cosine of 2 times pi over 4. And so y equals cosine of, and the 2 and 4 is going to cancel, so I have pi over 2. Oh, that's a 2, doesn't look like 1. And so think about you're sitting way up here at pi over 2. Your ordered pair is 0, 1, and cosine talks about x, so y is going to be 0. So we could cross out anything that has a y value. So that's going to get rid of B and A. So it looks like we're really down to these final 3. So now we need to find y prime. Well, y prime would be the derivative of cosine of 2x is negative sine of 2x times the derivative of, let's see, the angle, which is going to be 2. And so here, notice we're going to have maybe a -2. We know we're going to have a negative value, so that's going to get rid of C. So now we've got to go plug in pi over 4. So y prime equals negative sine of 2 times pi over 4. And then times 2 out here. Well, sine of pi over 4, or we'll cancel these out first, sorry. Sine of pi over 2, right back up here, but now we're talking about the y part. So y prime equals negative times 1, and then times 2. So that's going to give me -2, and that's the piece that we needed. So here my correct answer should be E.